Modern manufacturing floors generate an immense volume of operational telemetry every second. Programmable logic controllers, or PLCs, constantly record this data. These industrial computers, along with power meters and sensors, track variables ranging from machine temperature to peak power demand. But the vast majority of this critical data gets trapped. It flows into isolated, localized dashboards that rely entirely on manual human observation to spot trends or errors. Plant managers are often left to navigate massive spreadsheets of raw numbers that lack the necessary context to trigger an immediate operational change. Storing terabytes of unanalyzed telemetry without an autonomous system to interpret it quickly becomes an operational liability rather than a strategic asset. The alternative to that chaos is surprisingly straightforward on the surface: a standard smartphone message from the E3X.ai platform. This is a real-time energy alert. Notice the reading of 409.87 kilowatts and the accompanying tie analysis. Unlike a rigid PLC alarm, a large language model has evaluated this load against historical operating conditions of 250 to 400 kilowatts to generate a specific operational directive. We are going to deconstruct this exact alert. By tracing it backward, we will see how the E3X.ai pipeline transforms raw field hardware data into specific executive actions. The true value of an industrial Internet of Things, or IIoT, architecture is proven exclusively by its ability to convert complex operational data into an immediate, accurate intervention. To understand how that alert arrived on a phone, we have to look behind the chat interface at the back-end orchestration layer. This is N8N, the platform's central nervous system, a visual workflow tool linking IT and operational environments. Moving left reveals the AI analysis node, powered by Llama 3.1. It receives a highly structured payload of current telemetry and historical context, not a blank prompt. The LLM processes this exact payload to diagnose the equipment state. Because its context window is constrained entirely by hard data, it provides accurate analysis without hallucinating false conclusions. The orchestrator's primary function is to frame the real-time engineering problem so the AI agent can solve it autonomously. But this raises a critical engineering question. How does the AI mathematically differentiate between a normal 409 kilowatt spike caused by high production volume and an actual machine failure? This scatterplot charts energy use against production volume, showing specific energy consumption, or SEC. A linear regression line establishes baseline efficiency. The visualization then shifts to a time series graph. This cumulative sum, or CUSUM, tracks hidden baseline deviations and inefficiencies that static thresholds miss. The AI agent utilizes these SEC and CUSUM statistical models to accurately contextualize the exact power alert we saw earlier. The system operates as a predictive intelligence engine, identifying these trends before they escalate into critical failures. To execute those SEC and CUSUM models in real time, the AI requires millisecond access to years of historical data. This brings us to Layer 2, the time series database. The workflow relies on InfluxDB, a specialized database optimized specifically for handling high volumes of time-stamped operational telemetry. Below that sits Layer 1, field connectivity. Software called Telegraph access the platform's senses, pulling raw Modbus or MQTT signals from physical hardware and structuring it for the database. This entire four-layer architecture is highly lightweight and deployable. As shown here in the terminal, all these essential services, InfluxDB, Telegraph, N8N, and Llama, are running locally via isolated Docker containers. Local edge-based deployment is an absolute necessity for industrial facilities. It ensures strict data security, zero latency, and sovereign control over their operational technology networks. The high-level analytical power of the AI is entirely dependent on this secure, continuous pipeline of edge telemetry. While facility engineers need to know about a 409 kilowatt load anomaly to fix a compressor, C-level executives operate on entirely different metrics. Executive leadership prioritizes cost optimization and regulatory compliance over raw power readings and flow rates. Layer 4 automates the translation of technical units into business metrics. Raw kilowatt-hour data enters a transformation block, splitting into two distinct outputs: TIBOT for financial tracking and CO2 for carbon emissions. These metrics immediately populate a high-level executive dashboard. This provides immediate visibility into ESG reporting, environmental, social, and governance criteria used to evaluate corporate sustainability, and the exact financial impact of energy efficiency projects. The ultimate role of the architecture is to seamlessly translate the technical language of machines into the strategic language of business and sustainability. Implementing a 4-layer AI architecture across a massive legacy facility appears highly risky and disruptive to daily operations. The recommended implementation methodology mitigates this operational risk by entirely avoiding the attempt to upgrade everything at once. Facilities achieve the best results by starting with a small, focused pilot project, restricted to a single utility system, like a heavy-duty chiller, or one specific production line. The process is simple. Establish the energy baseline, connect the edge devices, and allow the AI agent to prove measurable return on investment on that isolated system first. True digital transformation in manufacturing does not require a massive facility-wide overhaul. Instead, it is achieved through a series of targeted, AI-validated quick wins that scale organically across the entire enterprise.